Hello, I'm Wojtek Kuberski, CTO at NANIML, and today we're going to talk about the strategies to monitor LLM hallucinations. First, let's start with why should I be talking about it. So NANIML, the company that I'm the CTO of, we do classical machine learning monitoring, both as an open source package and a cloud tool. On top of that, we're now building a hallucination detection tool that will allow you to detect and reduce hallucinations in LLMs. And to do that, we read and evaluated more than 100 of machine learning papers that deal with LLM hallucination. We compared them against each other, and we have the results that we will show at the end of today's webinar. So let's get started with the agenda. First, we're going to discuss what is LLM monitoring, what are the pillars of LLM monitoring, and what is the role of hallucination detection there. Then we're going to focus on 4 most promising approaches to detecting hallucinations in large language models. First one, we're going to talk about how to use another LLM to detect hallucinations in, let's say, the main LLM by looking at the consistency of the results. Then we're going to talk about using another LLM to directly just evaluate whether the answer might be a hallucination or not, which is a surprisingly effective approach. And then we're going to talk about 2 different ways to use uncertainty quantification when we look at token probabilities to try to estimate whether a given sentence or a given phrase is hallucinated or not. And then at the end, we'll see the results of our experiments when we compared different approaches from the academia, and we'll see which one actually performs best. So let's get started with the most important question, which is what is LLM monitoring? So there's basically 3 different monitoring types for LLMs, or 3 pillars that you should have to really make sure that your LLMs perform well in production. The first one is the infrastructure pillar, when we will monitor things like uptime and latency, just making sure that the infrastructure that powers the LLMs actually works well. The second one is monitoring LLM usage, when we'll talk about or we'll monitor things like conversation length, the sentiment of the user and the LLM, potentially the topics that are used to make sure that the LLM is used according to its intended purpose. If you have an LLM that should help your users purchase products, if most of the topics maybe are focused on solving homework problems, then it's probably not used the right way. And then the last pillar is the one that really ensures that LLMs are actually safe to use, and this is detecting hallucinations when we'll be trying to figure out what are the incorrect answers, incomplete answers, or vague answers given an LLM, flag them, and ideally replace them by better answers. So today we're going to be focusing only on the third pillar, the hallucination detection. And in terms of how we can evaluate whether an answer is a hallucination, we can look at it really from different kind of scope perspectives. The first one is when we'll just look at the full answer. So we have a prompt, let's say how to detect hallucinations in an LLM, and we could look at whether the entire answer contains hallucinations or not. This is an approach that's quite nice from the user perspective. However, it doesn't offer enough granularity to really make sure that you only remove the things that are hallucinations and you still keep most of the answers, so it's not very actionable. Then the second approach is to evaluate hallucinations per paragraph. So LLMs quite often answer in paragraphs, and we could just discard specific paragraph. This is a reasonable approach, and we see it in few papers. However, most of the papers and most of the approaches we've seen both in academia and in practice focus on sentence-level ground truth and sentence-level hallucination detection when we evaluate each sentence separately to see whether it's correct, full, and unambiguous. And then, of course, we could also look at just a single token and see whether that token is hallucinated or not. But for that, we're always kind of losing a bit of context and evaluating a single sentence in terms of a single word of whether it's hallucinated or not. It's not very meaningful for users. So this is generally an approach that's not taken either in literature nor in the real world. So now focusing on sentence level detection, we basically have the kind of approach or there's 4 different ways of detecting hallucinations, and they can be grouped into two high-level groups. In one, we're going to use another LLM, maybe the same LLM, but we're going to make another call to that LLM when we'll try to evaluate the quality of an answer and whether there is hallucinations with an LLM. Another one is we're going to focus on the uncertainty. And as I already mentioned in the agenda, there's four different specific and quite promising approaches. One, we'll look at the consistency between very similar answers to an LLM, and based on that, we'll try to see whether the original answer was hallucinated. Another one will ask an LLM to directly evaluate the answer that it has given before, and based on that, we'll hopefully be able to figure out whether it's hallucinating or not, because LLMs actually tend to know whether they are hallucinating or not, which is another surprising find from, I think, around a year ago. And then we have the uncertainty-based approaches, when we'll first focus on just looking at the output and trying to see how we can leverage the probability tokens, token probabilities, to really estimate whether a model is hallucinating or not. And then second, more advanced approach is we're going to not only focus on the probabilities of specific tokens, but we're going to look at the semantics, so the meaning of the answer, and whether the LLM is actually uncertain about the meaning of the answer it's giving. So let's get started with the LLM-based approach, the consistency. So how does it work? Let's start with an example. Imagine that we have the same prompt as always, how to detect hallucinations in an LLM. And what we're going to do is we're going to query the LLM multiple times with the same prompt, just adjusting, let's say, the random seed. There's also other things we can adjust, but let's focus on adjusting the random seed for the time being, and we'll just get multiple slightly different answers. And then we're going to compare those answers. That's another kind of potential lever that we can adjust, or a knob that we can turn in terms of how actually compare those. But let's abstract away from it now, and we'll just say that we compare those answers in some way, and we get a number at the end, and this number will represent how similar those answers are. And then intuitively, if the answers are very different, so the algorithm is so the LLM is very fragile in terms of how it gives the answers. If we just change the random seed, the answer is completely different, then it's quite likely that the LLM doesn't actually know the answer to the prompt, and instead is just hallucinating, coming up with some kind of random answer. And if the answers are very consistent, let's say it always gives the exact same answer, at least from the meaning perspective, then we can say that the answer is very likely to be correct. That's kind of the intuition behind the idea. So in terms of description, as already mentioned, we call an LLM multiple times, and we measure the consistency of the answer, or similarity between the answers. In terms of pros and cons, it does require multiple calls to LLMs, which tends to be quite expensive, which means that this is a use case, this is the type of, or the approach that we're going to avoid if cost is a factor, and it, generally speaking, is a factor for monitoring. We want to monitor with as little additional overhead as possible. Good thing about it, though, is that we don't need access to probabilities. So if we're working with an advanced LLM from, let's say, OpenAI, such as GPT-4, they unfortunately don't output token probabilities anymore. So we'll still be able to use that approach even if we don't have access to token probabilities. And we see that this approach to detecting hallucinations actually has quite a good performance. It's able to reasonably reliably detect hallucinations, even though it's quite expensive. So, as I mentioned, there are two different kind of knobs that we can turn for this algorithm. The first one is, how do we get different answers? So as I already mentioned, we can just change the random seed, and this is the approach that's generally preferred. But there's also other approaches we could potentially try. First, we could adjust the temperature and then see whether the similarity between the different answers actually changes. That's also another way to just get different answers, by slightly adjusting the temperature of an LLM. And another option is to use an LLM to paraphrase the prompt and use this new prompt again. And that introduces a bit more noise and requires yet an additional call to an LLM. So even though idea seems quite interesting at the first glance, it's generally not recommended to do it like that. Now, the second knob that we can use to really adjust the algorithm is how do we measure the consistency? The first option is we just use another LLM call with number of answers and say, give me an output between 0 and 1 that measures how consistent or how similar these answers are. Surprisingly, it works quite well. Yet again, we need another LLM call, but at least we're getting really good performance out of it. Another option is to use a simple metric such as cosine similarity between the tokens and the vectors of the tokens, and we'll just measure that vector and we'll measure cosine similarity between the original vector and all the other answers that were generated. And third, we could just use a smaller language model such as BERT to measure the similarity between the answers. And generally speaking, the best approaches here is either taking yet another LLM call, because then it's going to capture the semantic meaning of the answers quite well, or use BERT if we are quite cost conscious. And there's always going to be an example paper for which of the approaches we discuss. This time it's SelfCheckGPT. You can see the link to the archive here, and we're also going to share it at the end of the webinar. Now let's go to the second part, which is using LLMs to directly evaluate the answer that the original LLM gave. Again, let's start with the example. So we have the same prompt as always. We just get one answer, and then we're going to call an LLM with a specific handmade prompt that's going to ask whether, given the prompt and the answer, whether the answer is correct, whether it's complete, and whether it's grammatically sound. And we could, of course, ask for any other metric we want. That's just it. It's really kind of the simplest approach, and it's something that you could potentially code in a day. And interestingly enough, it only requires one additional code to an LLM, and it works quite well. But I'm getting ahead of myself, so let's talk about the details. As a description, we use an LLM to evaluate the quality of analysis, so we'll have one additional LLM call, which is much better than the previous approach, but we still are basically doubling our costs because we need to call an LLM twice, and maybe even more than that, because we're gonna put the entire answer, entire prompt, and additional prompt asking for the evaluation. So actually our prompt is gonna be longer than the original prompt, and it's gonna also be longer than the original answer. So we're more than doubling our costs for monitoring or detecting hallucinations that way compared to just using an LLM, which may be justified, but it's definitely a factor. Good thing, just as the previous method, because we're using an LLM directly to evaluate the answer, we can work with the raw text and we don't require access to probabilities. Another good thing about it is that we can include custom metrics if we want to do more than just detect hallucinations. And within the same LLM call, we can ensure that the answer is grammatically correct, that it's complete, and not only focusing on whether it contains hallucinations or not. And both in the literature and in our experiments, it gives really good performance. It's actually the best performing approach out of the ones we've examined. And example paper here is called just simple LLM-eval from last year. Again, you can check it after the webinar. In terms of the moving parts of this algorithm, there's really only one, which is which LLM. Actually, there's two. One is the prompt, but I'm going to skip the prompt engineering here because it's quite a complex topic and it's covered very well in the paper. And another moving part here is what LLM should we use as in the evaluator metric. So we could use a just simpler LLM, something that's really small, maybe it's one of the 7 billion parameters LLMs. It is cheap, but we don't get the same kind of expected level of performance as if we were using a more performant or more capable LLM. The other option, which is kind of the default idea, is to use the same LLM that we're using to actually get our answers for our use case. This is a very simple implementation because we're just calling the same LLM. We don't need to support another LLM, whether open source or closed source, and it's generally a preferred option. Another option would be to use a better LLM than the one we're using, which again increases the costs, and it's generally a bad idea because you could reduce hallucinations in the first place by just using the best LLM available to get your answers, if reducing hallucination is so important. And then you could indeed use it again, kind of following the number 2 here, to also evaluate the quality of the answer. So generally speaking, you should use either a simpler LLM that you have, if cost is a big factor, or the same that you're using for the main use case. And now we kind of covered the first part, which is the LLM-based approaches, and we're ready to go into the uncertainty-based approaches, where we're going to be working with token probabilities directly, and we're going to be doing things with them to try to estimate whether a model is hallucinating, which is definitely kind of a more advanced approach, but not necessarily better performing, which might be surprising. So let's get started with the output uncertainty quantification, where we're going to look at the token probabilities for each of the tokens in the answer. So here we see that we have the same answers. Always you can use another LLM, and for each of the tokens, so each of the words and each of the commas, full stops, etc., we're going to have a probability of that associated token. And here we just gave an example answer when you have specific probabilities, and we're gonna then use those probabilities in some way to create a confidence score that's gonna tell us how confident we are that this answer is not hallucinated. So we're now really getting a very specific answer that we want, using just the numbers. So we're not working directly with the text data, we are working with the token probabilities only. In terms of details and pros and cons, we will measure how certain LLM is of its answers. So we're basically asking the LLM itself of its confidence, and we're using this confidence because token probabilities are basically confidences of the LLM, and we're going to use those to evaluate the quality of the answer. So unfortunately, that means that it obviously requires answers to chosen token probabilities. So the tokens that were actually used in the answer, we need to have access to those, which might not be an option, for example, if you're using GPT-4. However, good news is that we don't require additional LLM calls because we're using this original answer to already get the uncertainty from the LLM itself. So we're still using an LLM, but without calling it additional times. That means that it's really cheap to run, and it gives okay performance. We're still able to find some of the hallucinations, and we don't get many false positives, but it is not perfect. An example paper here is looking for a needle in a haystack, which is a review paper that also features that approach. Okay, now we come to one of the kind of important questions here, which is what should be the uncertainty measure? How should we take all the numbers that we get, all the token probabilities, and then what algorithm we should actually use to output the probability of hallucination? And there's multiple options here. All of them are actually not perfect. So this is a really simple benchmark algorithm that only allows us to give a very simple, very cheap way to find hallucinations, but it's definitely not something that you should just use in production without any improvements. So we could just take the average token probability, which would tell us that this answer is not hallucinated. We could also slightly maybe more interesting idea, but very similar, is we should take geometric mean token probability, because the answers happen after each other and they are dependent on each other. So geometric mean intuitively makes more sense here. Or we could take the minimum token probability. So out of all the tokens, we'll just find the token with the minimum probability, and we output that as a probability of hallucination. We could also do any kind of function. We could potentially even train a model to take those numbers and output probability of hallucinations in a supervised fashion. But that's something that we'll cover maybe later on in another webinar. Right now, let's focus on very simple approaches. And here, what we noticed is both just the average token probability and geometric mean token probability are not really good at detecting hallucinations. And we're mostly focusing on the minimum token probability because it allows to find this one word or one part of the sentence that's actually wrong, which makes the whole sentence hallucinated. And now we're going to the fourth part, or four potential promising approach to detecting hallucinations, which is semantic uncertainty quantification. And it's going to be very similar to the previous approach, but it's going to build up on it, and it's going to incorporate the meaning of the answer in the uncertainty quantification itself. So how we're going to do it? So here we start with a prompt. This prompt is going to be different to illustrate how we can actually go about this semantic uncertainty quantification. So trying to find whether the algorithm or the LLM is confident of the meaning of its answer that it gave. So let's say our prompt is, what is the capital of France? And then just here visualizing top 3 tokens for each answers and taking the probabilities, we could see that the answer is Paris is the capital of France. It could also answer the capital of France is Paris, or just capital of France is Paris, skipping the article. And then if we see that these answers, they will do something with these answers, we'll try to measure the different potential meanings, and we're gonna then try to incorporate that meaning into our uncertainty quantification. This might sound quite vague at this point, so let me first start by explaining what do I mean by being semantically equivalent. It means that the meaning of the answer is actually the same. So the first answer, the answer that the LLM originally gave is the capital city of France is Paris. And that answer is semantically equivalent to just saying Paris. It's just a bit longer, a bit less terse. But then we can have another answer, which is going to be very similar from the syntax perspective. So syntactically, it's going to be very, very similar, which is the capital city of France is Rome, which is exactly the same string of words before giving the actual answer. But answer 3 is actually hallucinated. So now, if you try to reason like a human, what you would like to do is you don't really care whether the model is uncertain between answer 1 and answer 2. Even if it's 50-50, you actually don't want this uncertainty to be measured in your hallucination, because you know that the model is not hallucinating if the only 2 answers that it is going to give is the same answer, but either shorter or longer form. Whereas if the model is uncertain between giving answer 1 and 3, you definitely want to flag it as hallucination, because that means that the model doesn't know whether the capital city of France is Paris or Rome. So we're going to take that intuition and we're going to try to quantify it somehow. Now, before we go into how we actually quantify it, I should actually switch the order of the slides, but that's for the next time. Here, let's talk about pros and cons. So we now require access not only to the chosen token probabilities, the ones that we actually got answered, but all the token probabilities. So for each of the tokens, we basically get like this ever-expanding tree when we get all the possible answers, or top 50 possible answers for the first token, second token, etc., which makes it rather expensive to run, and saying rather expensive is an understatement unless we really optimize it. Good thing is it still does not require additional LLM costs, because it just incorporates kind of the full uncertainty of the LLM, and it also incorporates the full semantic meaning of words, sentences, and paragraphs, which is just great. This is exactly what we want when we try to detect hallucinations. So this is really the key benefit of using this approach. And because of that, it does have good performance, sometimes even outperforming the LLM-based methods, not always though. And here the paper is just called Semantic Uncertainty. And again, here's the archive link that we'll share after the webinar. Now, how does it work? So basically, we're going to take the first answer and we're going to find all the possible paths through the tree that yield a semantically equivalent answer. And then we're going to treat the probability, that kind of sum of those possible paths through the tree, as equivalent. So if the answer is the capital city of France is Paris, then, and it has certain probability of happening, we're going to also add all the answers that are semantically equivalent. And how do we actually find the semantic equivalence? We'll discuss in a second. And then we're going to add all the semantically equivalent answers to that answers in terms of probability mass. And then we're going to use that to say whether the model is hallucinating or not. So here, of course, the problem is that if we were to do that through the entire tree, it would become absolutely infeasible to compute and to even traverse that tree because the tree would be quite big. So what we want to do instead is we're going to focus on capturing, let's say, 90% of total probability mass of all the answers that the LLM could give. So we'll have to truncate those three, and we'll keep on truncating it as we keep on expanding it as well. So this is just a heuristic. It's quite early in terms of research there. The paper provides some ideas, but it is not very well defined at this point. And then how do we measure whether two answers to the kind of these three traversals, whether saying the capital city of France is Paris, are those two answers semantically equivalent? One thing we could do is ask an LLM, and another thing we could do, which is a bad idea, is to do cosine distance in the embedding space. And to just quickly illustrate why this is a bad idea, if you compare cosine distances between answer 1 and 2, the distance is going to be higher than between answer 1 and 3. So you really want to have something that actually understands the meaning of the words, which means calling an LLM or some other model. So in the end, we do have to call an LLM, but we still capture, on top of normal benefits of using an LLM, we still capture the semantic meaning of different answers, even the answers that were not chosen, which is definitely a good thing. So now we kind of covered the 4 different ideas in varying levels of depth, or 4 different approaches that we saw across literature. Now let's talk briefly about the experiment results. So first, how did we actually evaluate results? We used ground truth, so basically whether humans marked a given sentence as hallucinated or not, against the algorithm output of whether the model is hallucinating or not. And we compare those by just measuring the correlation between the human evaluations and the model evaluations. And we measure both the Pearson correlation and the Spearman correlation. So basically what you see here is using the LLM-eval scores. So the second approach we showed today, when we basically ask an LLM whether this answer is correct, relevant, informative, etc., versus the actual ground truth that the humans gave for that specific sentence. And we've seen that the correlations for Pearson are around 0.5. Averaging gives also kind of the best correlation, but it also is against the just average of ground truth, so it's not necessarily the best approach to take. And if we just look at the rank correlation, it's not great, but it's definitely significantly better than random, so we are able to detect a significant fraction of hallucinations. Now, if we compare it with another approach, which is just trying to find the sentence level probabilities, so we're just taking the minimum of each sentence level probability, so approach number 3, when we just do simple uncertainty quantification, we see that the correlation is generally much lower across the board, so we are still able to find some of the hallucinations, but we're unfortunately dealing with both reasonably high false positive rate when the algorithm would flag an answer as a hallucination, but the human wouldn't, and the other way around when the algorithm will miss an actual hallucination or a sentence flagged as hallucination by the human. So it's something that we can use, but as I already mentioned, it's just a benchmark. It's not something that you should use in production. And then another interesting kind of morsel of idea, of insight, is that we could potentially actually use both at the same time, because we see that if we compare the sentence level probabilities with LLM evaluation, they're not very correlated with each other. So there might be information in each of them that actually we could somehow leverage, put together, maybe using additional model that we would train to actually detect hallucinations better and use both of these outputs just as signals in the model. But that's the research that we're currently focusing on, and once we have some promising results, we'll definitely share that with the world. So now we're almost done. Let's just summarize what we learned today. So first of all, hallucinations can be reasonably reliably detected and reduced with current technology. We already have technology for that. Of course, the state of the art is evolving really, really fast, but there's already solutions that are quite promising. And then in terms of solutions that are actually potentially working, we have answer evaluation of LLM, when we will just directly ask another LLM to evaluate whether a given answer contains hallucinations or not, which is very good. It's moderately expensive. It does not need probabilities. It requires just one call to an LLM. And then we have our benchmark, which gives us something, but it's definitely not really good enough to put in production. So I really right now lean towards the answer evaluation with an LLM, which can be used for an LLM, whether open source or closed source. And it requires basically doubling the cost for using an LLM, which might be very well worth it if the use case is important enough. So that is really it. Thanks for listening. And if you want us to get in touch, once we have our MVP of the hallucination detection tool, leave your contact information here. And yeah, I hope to talk to you soon. You can also add me on LinkedIn, shoot me a message there if you prefer. And thanks a lot for listening again, and see you next time.